Everything ends. Not eventually, not maybe, not under certain conditions. Everything. Every star currently burning in the night sky will go dark. Every planet will cool and die. Every galaxy will drift beyond the reach of every other galaxy. Every atom will eventually decay. Every quantum fluctuation in the fabric of space-time will eventually cease. The universe itself, all 93 billion light-years of the observable cosmos, all 2 trillion galaxies, all the matter and energy and dark matter and dark energy that together constitute everything that exists, will come to an end. Not with a bang, not with a dramatic collision or a sudden reversal, but in one of several scenarios that physics currently considers the most plausible, and each of them is, in its own way, more disturbing than the last. We do not talk about this enough. We talk about the Big Bang, the beginning, the extraordinary creative and generative event that produced space and time and matter and energy from a state our physics cannot fully describe. We find the beginning easier to contemplate than the ending. But the ending is real. The ending is coming. And understanding how the universe ends, following the physics from where we are now, across timescales so vast they make the current age of the universe feel like an opening sentence, reveals something extraordinary about the nature of time, entropy, and what it means to exist in a cosmos that has a finite duration. The ending is not a single event. It is a sequence, a long, slow, layered unwinding that begins with the death of stars and ends with something so total, so complete, so final that even the concept of ending becomes difficult to apply. Come with us to the end of everything. It is the most important story ever told, and nobody makes it out alive. The universe is approximately 13.8 billion years old. In that time, it has been generous with stars, generous with light. The era we live in, right now, at this moment, is sometimes called the stelliferous era, the age of stars, the period in cosmic history when the universe actively produces, maintains, and shines through the light of hundreds of billions of stars in hundreds of billions of galaxies. It is, by any measure, the most luminous period the universe will ever know. And it is ending. Not quickly, not in any time frame relevant to human civilization, but on the timescales that cosmology deals in, the timescales of trillions of years, the stelliferous era has an expiration date. Stars require fuel. Specifically, they require hydrogen, the simplest and most abundant element, to fuse into helium in their cores. This fusion process is what generates the energy that makes stars shine, and the universe's supply of hydrogen, while enormous, is not infinite. Over time, as star after star is born and lives and dies, the available hydrogen in galaxies is consumed. Some is locked up in the remnants of dead stars, white dwarfs, neutron stars, and black holes, never to participate in fusion again. Some is ejected into intergalactic space, too diffuse to collapse into new stars. The rate of star formation in the universe has already been declining for roughly 10 billion years. The peak of star formation, the era when the universe was producing the most new stars per year, occurred about 10 billion years ago. We are already on the declining side of that curve. In roughly 100 trillion years, 10,000 times the current age of the universe, the last star will form. After that, no new stars. The existing stars will continue to burn for their natural lifespans. The most massive stars, which burn brightest and fastest, are already gone. Stars like our Sun burn for roughly 10 billion years, and the longest-lived stars, the smallest, dimmest red dwarf stars, barely hot enough to sustain fusion, will burn for up to 10 trillion years. 10 trillion! Long after our Sun has swelled into a red giant and consumed the inner planets and eventually cooled into a white dwarf, long after every Sun-like star in the Milky Way has extinguished itself,
Long after the night sky as we know it has gone entirely dark, those tiny, dim red dwarf stars will still be burning. But eventually, even they exhaust their fuel. The last star in the universe will go out, quietly, without witness, without ceremony. And the universe will enter a darkness it has not known since the cosmic dark ages that preceded the first stars. Except this time, the dark ages will not end. There will be no more hydrogen to collapse, no more stars to ignite, no more light. Just the remnants of what burned. White dwarfs cooling slowly over trillions of years, neutron stars spinning down, and black holes, patient, massive, enduring black holes, the last concentrated masses in a cooling, darkening cosmos. This era, after the last star dies and before the last black hole evaporates, is sometimes called the degenerate era. The universe, populated by the cooling corpses of dead stars, drifting in an increasingly dark and cold, expanding space. It lasts a very long time.
After the stars are gone, black holes rule. Not dramatically, not actively. They do not hunt or consume anything at this point. They simply exist. Dense, massive, patient. The most durable structures the universe ever produced. While stars burn for millions or billions or even trillions of years, black holes endure for timescales that make stellar lifetimes look trivial. A black hole with the mass of the Sun, a stellar mass black hole, would take approximately 10 to the 67th power years to evaporate through Hawking radiation. That is a 10 followed by 67 zeros. A supermassive black hole, like the 4 million solar mass Sagittarius A star at the center of our galaxy, would take approximately 10 to the 87th power years. 10 to the 87th power. To put that in perspective, the current age of the universe, 13.8 billion years, is approximately 10 to the 10th power years, 50 million times more than that. Supermassive black holes outlast the stars by so incomprehensible a margin that trying to express the ratio in meaningful terms becomes almost impossible. But what is Hawking radiation? In 1974, the physicist Stephen Hawking used quantum mechanics to show that black holes are not perfectly black, that at the event horizon, quantum effects cause pairs of virtual particles to appear spontaneously. One particle inside the horizon, one outside. The particle outside escapes as radiation. The particle inside effectively subtracts from the black hole's mass. Over time, over unimaginably vast time, a black hole loses mass through this process. Slowly at first, faster as it shrinks and its temperature increases, until in its final moments, the black hole evaporates completely in a burst of Hawking radiation. Every black hole in the universe will eventually evaporate, including the supermassive ones at the centers of galaxies, including the largest black holes ever formed. All of them, patient beyond all patience, enduring beyond all endurance, and then gone, evaporated. Their mass converted to radiation scattered into a universe that has grown so cold and so diffuse that even this final flicker of energy has nowhere significant to go. And when the last black hole evaporates, when the last concentrated mass in the universe releases its final burst of Hawking radiation into the void, what remains? What remains is called the heat death of the universe. The name is somewhat misleading. It does not mean the universe dies from heat. It means the opposite. It means the universe reaches a state of maximum entropy, thermodynamic equilibrium, in which no more energy can flow. No temperature gradients, no concentration of energy anywhere greater than anywhere else, no process that converts one form of energy into another, no work, no change. In a state of maximum entropy, the universe is the same temperature everywhere, effectively zero.
a fraction of a degree above absolute zero, as the last photons and particles spread out to fill the expanding void. No stars, no planets, no black holes, no atoms of note. Just an increasingly dilute gas of photons and leptons, electrons and positrons and neutrinos, drifting through an expanding space that continues to grow even as it contains less and less of anything. The universe does not stop, it just stops doing anything. And this state persists forever, or at least for a timescale that might as well be forever from any finite reference point. Except there are theories. There are models of what might happen even after the heat death, even after the last black hole evaporates, even after entropy has reached its maximum. One is called quantum fluctuation revival. In a universe at maximum entropy, containing nothing but an extremely dilute sea of particles and photons and endless empty space, quantum mechanics allows for the possibility of spontaneous random fluctuations, random reassemblings of particles into structures, given enough time. And we are talking about timescales so large that the entire history of the universe from Big Bang to heat death would be a rounding error. Quantum fluctuations could theoretically produce a particle, a hydrogen atom, a molecule, a star, even improbably beyond all imagination, a brief self-aware structure that experiences one moment of consciousness before dissolving back into the void. These are sometimes called Boltzmann brains, named after the physicist Ludwig Boltzmann. Random quantum assemblages of matter complex enough to briefly constitute a brain and have a single moment of experience. They are extraordinarily improbable. Even in a universe of infinite time, they would be vanishingly rare. But infinite time is very long, and given infinite time, even the vanishingly improbable becomes inevitable. There is another scenario, the Big Rip. If dark energy strengthens over time, if the force accelerating the expansion of the universe is not constant but growing, then the expansion itself may eventually overcome not just gravitational forces, but electromagnetic forces and nuclear forces too. In the Big Rip scenario, the accelerating expansion becomes so extreme that in the final moments before the end, galaxies are torn apart, then solar systems, then planets, then atoms, then the protons within atomic nuclei, then quarks. Everything ripped apart by the expanding fabric of space-time itself, on a specific schedule, galaxies going first, then solar systems, then planets, then molecules, then atoms, then protons. All of it destroyed, all of it simultaneously, at every scale, everywhere at once. And there is the Big Crunch. If dark energy is not permanent, if it weakens or reverses, the expansion of the universe could slow, halt, and then approach. The universe would contract, galaxies would merge, gas clouds would heat as the universe compressed. Eventually, everything would approach each other in an ever hotter, ever denser state, a mirror image of the Big Bang, but in reverse. A cosmic compression that ends in a singularity, the universe collapsing back to a point. And then, perhaps another Big Bang, perhaps a cyclical universe bouncing between expansions and contractions across infinite time. Each bounce a new cosmos, each cosmos a new chapter. Or perhaps just an end. The final full stop at the end of the longest sentence ever written.
The universe will end. Under one scenario or another, the heat death, the Big Rip, the Big Crunch, or something we have not yet imagined, everything that currently exists will be gone. Every star, every galaxy, every atom, every structure, every pattern, every concentration of energy that the universe spent 13.8 billion years building, gone. This is the most certain long-term prediction in all of science. Not certain in its details, not certain in its timeline, not certain in which of the possible endings turns out to be the actual one, but certain in its direction. The universe is running down. Entropy increases, order disperses, Energy concentrates and then dilutes. Stars burn and die. Black holes evaporate. The universe cools and expands and eventually reaches the stillest, coldest, most uniform state physically possible. And then it stays there. For a time or forever that no number we have access to can properly represent. You might think this should be devastating, that knowing the universe ends, knowing that everything we have ever built and loved and discovered and created is temporary, should drain the meaning from every human endeavor. That painting a picture, or raising a child, or building a civilization, or writing a symphony is pointless, because the universe will eventually be too cold and dark to remember any of it. But this conclusion requires a very particular and very questionable assumption. It requires that the value of something depends on whether it lasts forever. And it does not. A meal does not become less nourishing because it ends. A conversation does not become less meaningful because it concludes. A friendship does not become less real because both friends